1,000 years in temperate and arid lands. Many of the most important developments in absolute dating have come from the use of what one might call radioactive clocks, based on that widespread and regular feature in the natural world, radioactive decay. The best known of these methods is radiocarbon, today the main dating tool for the last 50,000 years or so. The main radioactive methods for periods before the timespan of radiocarbon are potassium-argon, uranium series, and fission-track dating. Thermoluminescence overlaps with radiocarbon in the time period for which it is useful, but also has potential for dating earlier epochs, as do optical dating and electron spin resonance, all being trapped electron dating methods that rely indirectly on radioactive decay. Radiocarbon dating. Radiocarbon is the single most useful method of dating for the archaeologist. As we shall see, it has its limitations, both in terms of accuracy and the time range it covers. Archaeologists themselves are also the cause of major errors, through poor sampling procedures and careless interpretation. Nevertheless, radiocarbon helped archaeologists to establish for the first time a reliable chronology of world cultures, transforming our understanding of the past. History and basis of method. In 1949, the American chemist Willard Libby published the first radiocarbon dates. During World War II, he had been one of several scientists studying cosmic radiation, the subatomic particles that constantly bombard the Earth, producing high-energy neutrons. These neutrons react with nitrogen atoms in the atmosphere to produce atoms of carbon-14, or radiocarbon, which are unstable because they have 8 neutrons in the nucleus instead of the usual 6 as for ordinary carbon. This instability leads to radioactive decay of 14C at a regular rate. Libby estimated that it took 5,568 years for half the 14C in any sample to decay its half-life, although modern research indicates that the more accurate figure is 5,730 years. Libby realized that the decay of radiocarbon at a constant rate should be balanced by its constant production through cosmic radiation, therefore, the proportion of 14C in the atmosphere should remain the same throughout time. This steady atmospheric concentration of radiocarbon is passed on uniformly to all living things through carbon dioxide. Plants take up carbon dioxide during photosynthesis. They are eaten by herbivorous animals, which in turn are eaten by carnivores. Only when a plant or animal dies does the uptake of 14C cease, and the steady concentration of 14C begin to decline through radioactive decay. Knowing the decay rate or half-life of 14C, Libby recognized that the age of dead plant or animal tissue could be calculated by measuring the amount of radiocarbon left in a sample. Libby's great practical achievement was to devise an accurate means of measurement. Traces of 14C are minute to start with, and are reduced by half after 5730 years. After 23,000 years, therefore, only 1/16 of the original tiny concentration of 14C is available to be measured in the sample. Libby discovered that each atom of 14C decays by radioactive clocks. The principles of radioactive decay. Like most elements occurring in nature, carbon exists in more than one isotopic form. It has 3 isotopes, 12C, 13C, and 14C. The numbers correspond to the atomic weights of these isotopes. In any sample of carbon-98, 9% of atoms are of 12C type and have 6 protons and 6 neutrons in the nucleus, and 1.1% are of the 13C type with 6 protons and 7 neutrons. Only one atom in a millions of atoms of carbon will be that of the isotope 14C with 8 neutrons in the nucleus. This isotope of carbon is produced in the upper atmosphere by cosmic rays bombarding nitrogen, and it contains an excess of neutrons, making it unstable. It decays by the emission of weak beta radiation back to its precursor isotope of nitrogen 14N with 7 protons and 7 neutrons in a nucleus. Like all types of radioactive decay, the process takes place at a constant rate, independent of all environmental conditions. The time taken for half of the atoms of a radioactive isotope to decay is called its half-life. In other words, after one half-life, there will be half of the atoms left, after two half-lives, 1/4 of the original quantity of isotope remains, and so on. In the case of 14C, the half-life is now agreed to be 5,730 years. For 238U, it is 4,500 million years. For certain other isotopes, the half-life is a minute fraction of a second. But in every case, there is a regular pattern to the decay. 4.18 radiocarbon is produced in the atmosphere and absorbed by plants through carbon dioxide, and by animals through feeding off plants or other animals. Uptake of 14C ceases when the plant or animal dies. 4.19 After death, the amount of 14C decays at a known rate. Measurement of the amount left in a sample gives the date. Part 1. The Framework of Archaeology. Releasing a beta particle, and he succeeded in counting these emissions using a Geiger counter. This is the basis of the conventional method still employed by many radiocarbon laboratories today. Samples usually consist of organic materials found on archaeological sites, such as charcoal, wood, seeds, and other plant remains, and human or animal bone. The accurate measurement of the 14C activity of a sample is affected by counting errors, background cosmic radiation, and other factors that contribute an element of uncertainty to the measurements. This means that radiocarbon dates are invariably accompanied by an estimate of the probable error, the plus-minus term attached to every radiocarbon date. One advance on the conventional method came with the introduction in some laboratories in the late 1970s and early 1980s of special gas counters capable of taking measurements from very small samples. In the conventional method, one needed C5G of pure carbon after purification, which means an original sample OFC 10, 20G of wood or charcoal, or 100, 200G of bone. The new equipment required only a few hundred milligrams of charcoal. Increasingly, the accelerator mass spectrometry method is becoming the dominant technique used in radiocarbon dating. This requires smaller samples still. AMS counts the atoms of 14C directly, disregarding their radioactivity. The minimum sample size is reduced to as little as 5-10 milligrams, thus enabling precious organic materials, such as the Turin Shroud, to be sampled and directly dated, and making feasible the direct dating of pollen. Initially, it was hoped that the datable timespan for radiocarbon using AMS could be pushed back from 50,000 to 80,000 years, although this is proving difficult to achieve, in part because of sample contamination. Calibration of radiocarbon dates. One of the basic assumptions of the radiocarbon method has turned out to be not quite correct. Libby assumed that the concentration of 14C in the atmosphere has been constant through time, but we now know that it has varied, due to changes in the Earth's magnetic field and that of the Sun. The method that demonstrated the inaccuracy Turing dating has also provided the means of correcting or calibrating 14C dates. Radiocarbon dates obtained from Turing show that before about 1000 BC dates expressed in radiocarbon years are increasingly too young in relation to true calendar years. In other words, before 1000 BC trees were exposed to greater concentrations of atmospheric 14C than they are today. By obtaining radiocarbon dates systematically from the long Turing master sequences of bristlecone pine and oak, scientists have been able to plot radiocarbon ages against Turing ages to produce calibration curves enabling radiocarbon dates to be corrected into calendar time. This calibration effort has come to be called the second radiocarbon revolution. Turing-dated wood provides a direct measure of atmospheric radiocarbon and therefore represents the best material possible for the calibration curve. At present, these records extend back to 12,600 years ago. The trairings come from U.S. bristlecone pine, German pine and oak, and Irish oak. Beyond this, scientists must rely on other proxy records to calibrate radiocarbon. These consist predominantly of foraminifera from varve-counted marine sediments and uranium-thorium-dated pristine corals. The latest in Cal 13 curve now reaches back to 50,000 calories BP. Again, the curve shows that there can be significant offsets between radiocarbon and calendar years, of up to 4,000 to 5,000 years in some parts of the timescale. Data to strengthen this curve have come from the Lake Suigetsuvarved lake sediment record in Japan and Australasian trees, whose age extends beyond 20,000 BP. There are short-term wiggles in the curve and occasionally sections of the curve that run so flat that two samples with the same age in radiocarbon years might in reality be 400 years apart in calendar years, a problem particularly irksome for dating in the Iron Age period 800–400 BC. For 0.20, the wiggles of the Cal 13 calibration curve over the last 9,000 years. The straight line indicates the ideal 1:1 timescale. Between c. 355 and 300 years ago, during the so-called Maunder minimum, there were very few sunspots recorded, indicating lower solar activity. This in turn affected Earth's magnetic field, causing radiocarbon production to rise, and giving us the steep section in the calibration curve at this time. When dating methods and chronology for. When calibrating a radiocarbon date, it is important that both the measured radiocarbon date and its error estimate are calibrated. This produces an age range in calendar years. Some of the ranges will be narrower and more precise than others, depending on where on the curve the radiocarbon date and its error estimate falls. Several software programs are now available that allow the user to generate computer-derived calibrations. Bayesian methods involve additional non-chronometric archaeological information that is analyzed using statistical methods to produce new probability distributions. Publication of radiocarbon dates. Radiocarbon labs provide an estimate of age based on their measurement of the amount of radiocarbon activity in a sample. The level of activity is converted to an age expressed in number of years between the death of an organism and the present. To avoid confusion caused by the fact that the present advances each year, laboratories have adopted AD 1950 as their present, and all radiocarbon dates are quoted in years BP or years before the present, meaning before 1950. Thus, in scientific publications, radiocarbon dates are given in the form 3700 plus or minus 100 BP. The first figure is the radiocarbon age BP, next is the associated measurement error. Finally, in parentheses is the laboratory analysis number. Each laboratory has its own letter code. As discussed above, various factors prevent the precise measurement of radiocarbon activity in a sample and, consequently, there is a statistical error or standard deviation associated with all radiocarbon dates. Radiocarbon dates are quoted with an error of 1 standard deviation. For a date of 3700 plus or minus 100 BP, this means that there should be a 68.2% probability, 2 chances in 3 that the correct estimate of age in radiocarbon years lies between 3800 and 3600 BP. Since there is also a 1 in 3 chance that the correct age does not fall within this range, archaeologists are advised to also consider the date range at 2 standard deviations, i.e. to double the size of the standard deviation, so that there will be a 95% chance that the age estimate will be bracketed. For example, for an age estimate of 3700 plus or minus 100 BP, there is a 95.4% chance that the radiocarbon age of the sample will lie between 3900 and 3500 BP. Calibrated dates should be reported as Cal-BC AD or Cal-BP, and it is important that the relevant calibration dataset should be reported as well, since calibration datasets are periodically revised and extended. Therefore, the conventional radiocarbon age, that is to say the radiocarbon age BP, should be reported, along with the accompanying stable carbon isotope measurement. The conventional age, once measured, will never change, but calibrations and calibrated dates do. where the archaeologist is discussing absolute chronology, generally perhaps using radiocarbon alongside other methods of dating, including historical ones. It seems logical to employ the simple BC add system, provided an attempt has been made to calibrate any radiocarbon dates. And that this is stated clearly at the outset. Contamination and interpretation of radiocarbon samples. Although radiocarbon dates have certain inescapable levels of error associated with them, erroneous results are as likely to derive from poor sampling and incorrect interpretation by the archaeologist as from inadequate laboratory procedures. The major sources of error in the field are as follows. 1. Contamination before sampling. Problems of contamination of the sample within the ground can be serious. For instance, groundwater on waterlogged sites can dissolve organic materials and also deposit them, thus changing the isotopic composition. The formation of mineral concretions around organic matter can bring calcium carbonate entirely lacking in radiocarbon, and thus fallaciously increase the apparent radiocarbon age of a specimen by effectively diluting the 14C present. These matters can be tackled in the laboratory. 2. Contamination during or after sampling. All radiocarbon samples should be wrapped in aluminium foil and sealed within a clean container such as a plastic bag at the time of recovery. They should be labeled in detail at once on the outside of the container. Cardboard labels inside can be a major source of contamination. The container should be placed inside another, one plastic bag, well sealed. Inside another bag separately sealed can be a sound procedure for most materials. But wood or carbon samples that may preserve some triggering structure should be more carefully housed in a rigid container. Wherever possible, exclude any modern carbon, such as paper, which can be potentially problematic. However, modern roots in earth cannot always be avoided. In such cases, it is better to include them, with a separate note for the laboratory, where the problem can be compensated for. Application of any organic material later, such as glue or carbowax, is likewise disastrous, as is continuing photosynthesis within the sample. The relevant containers should be stored in the dark. A green mold is not uncommon in sample bags on some projects. It automatically indicates contamination of a Gaussian or normal distribution on the y-axis. This distribution is transformed, using the calibration curve and its associated error, into a probability distribution on the x-axis, representing calendar years. The parts of the radiocarbon distribution that have higher levels of probability also have a higher probability on the calendar scale. The calibration curve is full of steep and sometimes wiggly sections, including sections with plateaus where the amount of radiocarbon in the atmosphere remains the same over long periods of time. Here the calibration precision is always wide. Even dating single samples at high levels of precision or dating multiple samples cannot substantially improve the situation. Sometimes, however, where the elapsed time between How to calibrate radiocarbon dates. Series of datable events is known. It is possible to obtain a very precise date by wiggle matching. This is most frequently applied to radiocarbon dates from tree rings. A series of radiocarbon measurements made of several radiocarbon samples with a known number of years between them allows the resulting pattern of changes in radiocarbon content over time to be directly matched statistically with the wiggles in the calibration curve. This can provide a date for the felling date of the tree to within 10 or 20 years. Alternatively, where other information such as a set of radiocarbon figures linked by stratigraphy exists, it is now possible to use Bayesian statistics to combine all the known data. Calibration programs and curves can be obtained directly from the radiocarbon website at Radiocarbon laboratories will generally supply calibrated dates of their samples, but archaeologists may need to calibrate raw radiocarbon dates themselves. The calibration curve, part of which is shown in the diagram on page 148, illustrates the relationship between radiocarbon years and samples dated in actual calendar years. The two lines of the calibration curve indicate the width of the estimated error at one standard deviation. In order to find the calibrated age range of a radiocarbon sample, a computer program is most often used. There are several that are freely available on the internet. With Oxcal, a simple plot is generated of a single calibrated result, such as in the diagram below. In this example, one can see the radiocarbon date of 470 plus or minus 35 BP is represented in the form. For 0.21, this diagram shows the calibration of a single radiocarbon date using Oxcal. The y-axis shows the probability distribution of the radiocarbon age 470 plus or minus 35 BP. The measured age is calibrated using the Cal09 calibration curve, forming the new probability distribution in gray, which is the calibrated age. Age ranges at 68.2 and 95.4% probability are given. When? Dating methods and chronology for 3. Context of deposition. Most errors in radiocarbon dating arise because the excavator has not fully understood the formation processes of the context in question. Unless it is appreciated how and when the organic material came to be buried and find its way to the position where it was found, precise interpretation is impossible. The first rule of radiocarbon dating must be that the excavator should not submit a sample fitting unless he or she is sure of its archaeological context. 4. Date of context. Too often, it is assumed that a radiocarbon determination, e.g. on charcoal, will give a straightforward estimate for the date of the charcoal's burial context. However, if that charcoal derives from roof timbers that might themselves have been several centuries old when destroyed by fire, then one is dating some early construction, not the context of destruction. There are numerous examples of such difficulties, one of the most conspicuous being the reuse of such timbers or even of fossil wood whose radiocarbon date could be centuries earlier than the context in question. For this reason, samples with a short life are often preferred, such as twigs of brushwood or charred cereal grains that are not likely to be old at the time of burial. A strategy for sampling will recall the wise dictum that one date is no date, several are needed. The best dating procedure is to work toward an internal relative sequence, for instance, in the stratigraphic succession on a well-stratified site such as the Gatecliff Shelter, Monitor Valley, Nevada, excavated by David Hurst Thomas and his associates. If the samples can be arranged in relative sequence in this way. For 0.22, samples for radiocarbon dating should be obtained, wherever possible, from the kind of context shown here where the material to be dated has been sealed in an immobilizing matrix. The stratigraphic context of the sample must be clearly established by the excavator before the material is submitted to the laboratory for dating. 4.23 Master Profile for Gatecliff Shelter, Nevada, produced by David Hurst Thomas, showing how dates derived from radiocarbon determinations cohere with the stratigraphic succession. Grain in mud brick. Charcoal in baked clay. Organic materials sealed in refuse pit. Bone under stone. Insect remains in lake bed. Bayesian analysis can tie dates down to this level. In most cases, the method allows radiocarbon to resolve chronologies to within a century.as. With any such statistical approach, the outputs depend strongly on the assumptions made, and so it is often necessary to see how robust the conclusions are against different theoretical models. Dating British Neolithic long barrows. In most archaeological sites, long-lived wood is either not preserved or not very closely associated with the activity of interest. However, in carefully excavated sites where wood is present and of interest, as in the British Neolithic, it is possible to use the relationship between samples found on sites to improve the precision of the dating. Stratigraphic information can allow us to deduce the sequence of dates. In almost all cases, we have groups of samples that are all from one particular period. Bayesian analysis, improving the precision of radiocarbon chronologies. All this information can be used to construct site models and to compare dates between different sites. This has been used to great effect in the study of British Neolithic long barrows, where the precision of the chronology is such that we are able to understand the sequence of events at the level of individual human generations. While the individual radiocarbon dates gave a misleading impression that many of these monuments had long histories, the Bayesian analysis showed that in actuality this type of monument was a much more transient phenomenon. Wood samples relating to the eruption of Thera. Where tree rings cannot be dated dendrochronologically, wiggle match dating can be used. This involves radiocarbon dating samples from a tree ring sequence and then fitting the results to the calibration curve using Bayesian methods to determine the best fit, mimicking the shape of the calibration curve. Since the relative calibration of radiocarbon dates is necessary to correct for past variations in the radiocarbon content of the atmosphere. However, there is a limit to the precision that can be achieved, a limit that depends on the period in question. At best, for single samples a range of 1 to 2 centuries is possible. For some periods the resolution is even lower. This limitation, however, can be overcome if we are able to combine the information from the radiocarbon measurements with not only the data from the calibration curve, but also information on the relative age of samples and their groupings, usually derived from excavation stratigraphy. Bayesian statistics provides the framework for this, and there is software available to do the analysis. Bayesian analysis can significantly improve the precision of the radiocarbon method and has been applied to a range of different types of problem, including single-site chronologies, sedimentary sequences, and regional chronologies. In all cases, the analysis fits the radiocarbon dates onto the calibration curve, taking into account the other information we have about the samples. Increasing the amount of specific information and the number of radiocarbon dates improves the resolution. The calibration curve itself has a resolution of about a decade and, at its best, 4.24 a summary of probability distributions of dated events in 5 key Neolithic sites in southern Britain. Note the short amount of elapsed time between many of the start and end dates for the use of the monuments. Prior to careful radiocarbon dating and Bayesian modeling, most of the sites were thought to be in use for hundreds of years. Now archaeologists realize that in some cases only 1 or 2 human generations elapse from construction to abandonment. When? For. With the lowest unit having the earliest date and so on, then there is an internal check on the coherence of the laboratory determinations and on the quality of field sampling. Some of the dates from such a sequence may come out older than expected. This is quite reasonable as explained above. Some of the material may have been old at the time of burial. But if they come out younger than expected, then there is something wrong. Either some contamination has affected the samples, or the laboratory has made a serious error, or, as not infrequently happens, the stratigraphic interpretation is wrong. It should be noted that for marine organisms, or for human or other faunal remains where the diet has been predominantly a marine one, radiocarbon dates are on average several centuries older than contemporary terrestrial dates. It is necessary in such cases to use a marine calibration curve. For human remains from Mesolithic Oronsay, on the west coast of Scotland, the adjustment is of the order of 400 years. Unfortunately, there are local variations in this effect, so that there is no universally applicable marine calibration curve, and care must therefore be taken when comparing dates derived from shell or other marine organisms with those based on terrestrial organic remains. Although many problems with radiocarbon dates may be attributed to the submitter, there is some evidence to suggest that radiocarbon laboratories themselves may be overestimating the precision of their own dates. In one comparative study, over 30 radiocarbon laboratories dated the same sample. While some estimated their errors within reasonable accuracy, others did not, and one laboratory produced systematic errors of 200 years. In general, it was seen that although radiocarbon laboratories might quote levels of precision of plus or minus 50 years, in fact it was safer to assume that their actual errors were plus or minus 80 years or more. As the interlaboratory study comprised an anonymous sample of some of the world's radiocarbon laboratories, the archaeological community has no way of knowing how widespread the underestimation of errors is or how systematically biased in their radiocarbon dates some laboratories are. Archaeologists would be best advised to treat radiocarbon laboratories like purveyors of any other service and request evidence that they deliver both the accuracy and the precision they purport to offer. Many laboratories are aware of their past biases and now quote realistic statements of precision that need not be regarded as underestimates. Furthermore, often they may be approached to quote new and more realistic errors for their earlier dates. Applications: the impact of radiocarbon dating. If we seek to answer the question when, in archaeology, radiocarbon has undoubtedly offered the most generally useful way of finding an answer. The greatest advantage. Sequence is known, and the last trayring where latest rings can be identified, a very precise date can sometimes be determined. A good example of this relates to the date of the eruption of Thera. Wood from an ornate chair found at Miletos lay under the tephra layer and so should predate the eruption. The dated rings, spanning 7 decades, fit the shape of the calibration curve and indicate a final date for the most recent wood in the first half of the 17th century BC. An olive branch from Thera itself, thought to have survived right up to the eruption, yielded 4 radiocarbon dates that also fit the calibration curve and give a date within the latter half of the 17th century BC. In both cases, by using the known age difference between the radiocarbon samples, a dating precision of just a few decades is possible, something that could not have been achieved with single measurements on short-lived material. 4.25 match of radiocarbon date series from trayring sequences related to the eruption of Thera. The sample above is from a chair found at Miletos and should predate the eruption, whereas that below is from an olive tree at Thera itself that is thought to have grown right up to the eruption. Modeled date. Part 1. The framework of archaeology is that the method can be used anywhere, whatever the climate, as long as there is material of organic origin. Thus the method works as well in South America or Polynesia as it does in Egypt or Mesopotamia. And it can take us back 50,000 years, although at the other end of the timescale it is too imprecise to be of much use for the last 400 years. The use of the method on a single site has been illustrated by reference to the Gatecliff Shelter, Nevada. Another interesting application is the dating of the Upper Paleolithic paintings in the Chauvet Cave, southern France, discovered in 1994. Tiny samples taken from several drawings done with charcoal were dated, producing a series of results centered around 31,000 BP, far older than anticipated. Almost all radiocarbon dating of Ice Age cave art has so far been done by a single laboratory and requires independent verification. In addition, all results over 30,000 BP are subject to ever greater levels of error and uncertainty. As many aspects of Chauvet Cave's art, its content, styles, sophistication, and techniques cast doubt on the early dates, and in view of their enormous implications for the development of cognitive abilities, it is necessary to subject cave art dating to verification by using multiple laboratories, splitting samples where possible. On a wider scale, radiocarbon has been even more important in establishing for the first time broad chronologies for the world's cultures that previously lacked timescales of their own. Calibration of radiocarbon has heightened, not diminished, this success. It has also helped assert the validity of an independent radiocarbon chronology for prehistoric Europe, free from false links with the Egyptian historical chronology. Radiocarbon dating by the AMS technique has opened up new possibilities. Because only minute samples are required, it is now possible to date a single grain of wheat or a fruit pip. An AMS reading on a grape pip from Hambledon Hill, southern Britain, shows that grapes, and probably vines as well, had reached this part of the world by 3500 BC in calendar years, over 3,000 years earlier than had previously been supposed. Precious objects and works of art can also be dated non-destructively. In 4.26 A rhino painting in Chowvit Cave, whose art has been claimed to date to 31,000 years ago. These results remain highly controversial. 4.27 Part of the Turin Shroud, bearing the image of a man's body. Radiocarbon AMS dating has given a calibrated age range for the cloth of AD 1260-1390. 1988 AMS dating resolved the long-standing controversy over the age of the Turin Shroud, a piece of cloth with the image of a man's body on it that many genuinely believe to be the actual imprint of the body of Christ. Laboratories at Tucson, Oxford, and Zurich all placed it in the 14th century AD, not from the time of Christ at all. This remains a matter of controversy. AMS has been applied to organic material discovered in prehistoric paintings. For example, despite problems at Chowvit and elsewhere, sound results have been obtained from some French and Spanish Paleolithic caves where charcoal was used as a pigment in the paintings, as well as from plant fibers in paint in rock shelters in Queensland, and from human blood protein found in paint in Wargadamina Cave in Tasmania. Other methods for dating rock art are being explored. For example, layers of calcite that build up on top of images in caves may be datable by radiocarbon, and by uranium. Thorium oxalates also form deposits that are susceptible to radiocarbon dating. Radiocarbon looks set to maintain its position as the main dating tool back to 50,000 years ago for organic materials. For inorganic materials, however, thermoluminescence and other, new, techniques are very useful. Potassium-argon dating. The potassium-argon method is used by geologists to date rocks hundreds or even thousands of millions of years old. It is also one of the most appropriate techniques for dating early human sites in Africa, which can be up to 5 million years old. It is restricted to volcanic rock no more recent than around 100,000 years. Basis of method. Potassium-argon dating, like radiocarbon dating, is based on the principle of radioactive decay, in this case, the steady but very slow decay of the radioactive isotope potassium-40 to the inert gas argon-40 in volcanic rock. Knowing the half-life of 40 K, measuring the quantity of 40 AR trapped within a 10 G rock sample estimates the date of the rock's formation. A more sensitive variant of the method, which requires a smaller sample, sometimes a single crystal extracted from pumice, is known as laser fusion argon-argon dating. A stable isotope of potassium, 39 K, is converted to 39 AR by neutron bombardment of the sample to be dated. Both argon isotopes are then measured by mass spectrometry after their release by laser fusion. As the 40K-39K ratio in a rock is constant, the age of the rock can be determined from its 40 AR-39 AR ratio. As with all radioactive methods, it is important to be clear about what sets the radioactive clock to zero. In this case, it is the formation of the rock through volcanic activity, which drives off any argon formerly present. The dates obtained in the laboratory are in effect geological dates for rock samples. Happily, some of the most important areas for the study of the Lower Paleolithic, notably the Rift Valley in East Africa, are areas of volcanic activity. This means that archaeological remains often lie on geological strata formed by volcanic action, and hence suitable for KAR dating. In addition, they are often overlain by comparable volcanic rock, so that dates for these two geological strata provide a chronological sandwich, between the upper and lower slices of which the archaeological deposits are set. It has been shown, by argon-argon analysis of pumice from the eruption of Vesuvius in AD 79, that the method has a good degree of precision even for quite recent eruptions. Applications: early human sites. Olduvai Gorge in Tanzania is one of the most crucial sites for the study of hominin evolution, as it has yielded fossil remains of Australopithecus boisei, Homo habilis, and Homo erectus, as well as large numbers of stone artifacts and bones. Being in the Rift Valley, Olduvai is a volcanic area, and its 2 million-year chronology has been well established by KAR dating and ARAR dating of the relevant deposits of hardened volcanic ash and other materials between which the archaeological remains are found. The KAR method has also been immensely important in dating other early East African sites, such as Hadar in Ethiopia, as well as Atapuerca in Spain. Limiting factors. The results of KAR dating are generally accompanied by an error estimate, as in the case of other radioactivity-based methods. For example, the date of Tuf IB at Oldaway has been measured as 1.79 plus or minus 0.03 million years. An error estimate of 30,000 years might at first seem a large one, but it is in fact only of the order of 2% of the total age. The principal limitations of the technique are that it can only be used to date sites buried by volcanic rock, and that it is rarely possible to achieve an accuracy of better than plus or minus 10%. Potassium-argon dating is nevertheless a key tool in areas where suitable volcanic materials are present. Uranium series dating. This dating method is based on the radioactive decay of isotopes of uranium. It has proved particularly useful for the period 500,000, 50,000 years ago, which lies outside the time range of radiocarbon dating. In Europe, where there are few volcanic rocks suitable for dating by the potassium-argon technique, uranium series dating may clarify when a site was occupied by early humans. Basis of method. 2 radioactive isotopes of the element uranium decay in a series of stages into daughter elements. 2 of these daughter elements, thorium and protactinium, themselves also decay with half-lives useful for dating. The essential point is that the parent uranium isotopes are soluble in water, whereas the daughter products are not. This means, for instance, that only the uranium isotopes are present in waters that seep into limestone caves. However, once the calcium carbonate, with uranium impurities, dissolved in those waters is precipitated as travertine onto cave walls and floors, then the radioactive clock is set going. At the time of its formation, the travertine contains only water-soluble 238U and 235U. It is free of the insoluble 230th and 231 pascals isotopes. Thus the quantities of the daughter isotopes increase through time as the parent uranium decays, and by measuring the daughter-parent ratio, usually 230th 238U, the age of the travertine can be determined. The isotopes are measured by counting their alpha emissions. Each isotope emits alpha radiation of a characteristic frequency. In favorable circumstances, the method leads to dates with an associated standard error of plus or minus 12,000 years for a sample with an age of 150,000 years, and of about plus or minus 25,000 years for a sample of age 400,000 years. These figures can be greatly reduced by using thermal ionization mass spectrometry to measure directly the quantities of each isotope present. Such high-precision dates might, for instance, have an associated uncertainty of less than 1,000 years for a 100,000-year-old sample. Applications and limiting factors. The method is used to date rocks rich in calcium carbonate, often those deposited by the action of surface or groundwaters around lime-rich springs or by seepage into limestone caves. Stalagmites form on cave floors in this way. As early humans sometimes used caves and overhanging rocks for shelter, artifacts and bones often became embedded in a layer of calcium carbonate or in another type of sediment between 2 layers of the calcareous deposit. The difficulty of determining the correct order of deposition in a cave is one reason why the U-series method is prone to give ambiguous results. For this and other reasons, several layers of deposit in a cave need to be sampled and the geology meticulously examined. The method has nevertheless proved very useful. At the Pontnewydd Cave in North Wales, the lower breccia, which contained the bulk of the archaeological finds, there is shown by U-series dating to be at least 220,000 years old. And at the early human site of Atapuerca in Spain, U-series dating has been used successfully in conjunction with other methods such as potassium-argon. The uranium-thorium dating method is increasingly being applied to calcite layers in caves which overlie prehistoric imagery. While radiocarbon analysis can only yield results for organic pigments such as charcoal, dating the formation of calcite provides a minimum age for any imagery that lies beneath it. Recently, the method has been applied to calcite layers overlying imagery in several caves in northern Spain and has produced some startlingly early results. A red sign on the decorated ceiling of Altamira is at least 35,000 years old, while in El Castillo a hand stencil has a minimum age of 37,300 BP, and a red disc one of 40,800 BP. These results thus open up the possibility that some early motifs, perhaps including hand stencils, may be attributed to Neanderthals. Teeth can also be dated by this method, because water-soluble uranium diffuses into dentine after a tooth has become buried, although there are problems estimating the rate of uranium uptake through time. Nevertheless, TIMS U-series dating has been employed successfully to date mammalian teeth found in association with hominin skeletons in 3 Israeli caves, Tabun, Kafsa, and Sku-El, with dates in the range 105,000 to 66,000 years ago. 4.29 Examples of fission tracks, after etching. 4.28 Hand stencil from El Castillo Cave, Spain. Uranium-thorium dating of calcite layers overlying this stencil and others has produced very early results. The earliest stencil has a minimum age of 37,300 BP. It may, therefore, have been created by Neanderthals. Increasingly U-series dates are being used in conjunction with electron spin resonance dates using the same materials. Neanderthal individuals from Krapina in Croatia were dated by both methods using tooth enamel, both giving ages of around 130,000 years. Fission track dating. Fission track dating depends upon the spontaneous fission of radioactive uranium atoms present in a wide range of rocks and minerals, which causes damage to the structures of the minerals involved. In materials where 238U is present, such as volcanic and manufactured glasses, and minerals like zircon and apatite found within rock formations, the damage is recorded in pathways called fission tracks. The tracks can be counted. Dating the earliest West Europeans. The Sierra de Atapuerca, near Burgos in northern Spain, is a veritable treasure house of sites, mostly infill caves, that are rewriting the early prehistory of Western Europe. Archaeological sites have been known there since the 1860s, and the first excavations of Pleistocene tools and fauna occurred in the 1960s. However, the first discovery of fossil hominin remains came in the 1970s. Excavations have been ever more numerous and intensive since the 1980s, at first directed by Emiliano Aguirre, and subsequently by Juan Luis Arzuaga, José María Bermúdez de Castro, and Udal Carbonell. Even now, only a tiny fraction of the Sierra's contents have been investigated. Work will continue for decades if not centuries, and Atapuerca ranks as one of the world's most important archaeological areas. Dating Atapuerca. Chronology has always been at the forefront of work in these sites as increasingly early layers were exposed. In the face of widespread dismissal by the archaeological establishment, many conservative scholars were initially reluctant to abandon the belief that there was no human occupation of Europe before 500,000 years ago. A variety of techniques has been applied, from microfaunal analysis to radiocarbon, potassium argon, and uranium series methods. They have combined to present evidence of occupation which stretches back more than 1 million years. Of particular importance are levels TD4, TD5 and TD6 at the Grandolina site, which are dated c. 800,000, 1 million years ago. In 1994, the human remains and stone tools found in TD6 provided the first undeniable evidence for hominins in Europe during the Lower Pleistocene. The hominins were given a new species name, Homo antecessor. Electron spin resonance and uranium series dating of fossil teeth confirmed the Lower Pleistocene age of level TD6, while the same methods placed the lower half of TD8 at 600,000 and TD10 and TD11 between 380,000 and 340,000. These figures correlated well with the microfaunal dates to IN the Galeria site. The lowest layers have been dated to more than 780,000 years ago by means of 4.30 31 map of the site of Sierra de Atapuerca showing where the most important hominin fossil finds have been made. The skull of Homo antecessor, found at Grandolina, provided the first secure evidence that humans lived in Europe during the Lower Pleistocene period, nearly 1 million years ago, and so earlier than the close relative Homo heidelbergensis. Spainportugal Atapuerca. 4.32, 33 excavation at Grandolina. Now a World Heritage Site, the Sierra de Atapuerca is one of the most intensively investigated archaeological areas anywhere in the world. Bones from the Cima de los Huesos, some of the 5,500 human fossils found there, dating to more than 430,000 years ago. At least 30 individuals are represented, mainly adolescents and young adults, and every part of the human skeleton has been recovered. Paleomagnetism, while above is GIA, dated by electron spin resonance and uranium series to 350,000, 300,000, and GIV at 200,000. The Cima del Elefante has a deep stratigraphy, faunal, microfaunal, and paleomagnetic analyses here have shown that the lowest section, which has yielded stone flakes made by humans, dates to the Lower Pleistocene, more than 1 million years ago, while Phase 4 belongs to the end of the Middle Pleistocene. This enormous time span is probably due to the temporary closure of the cave in Phase 3, which caused a major hiatus in the accumulation of sediments. In 1998 it was announced that a human jaw together with stone tools had been recovered from layer TE9, which a number of methods analysis of rodents and insectivores, paleomagnetism, and burial dating placed at 1.1, 1.2 million years ago, making it the oldest and most securely dated record of human occupation in Europe. In the Cima de los Huesos, a combination of microfaunal analysis, electron spin resonance and uranium series methods has established that a speleothem that covers the deposit containing human bones dates to at least 430,000 years ago, while high-resolution uranium series dates have shown that the bodies were placed here about 600,000 years ago. Thermoluminescence dating. Thermoluminescence dating can be used to date crystalline materials buried in the ground that have been fired, usually pottery, but also baked clay, burnt stone, and in some circumstances burnt soil. But unfortunately it is a method that is difficult to make precise, and so it is generally used when other methods, such as radiocarbon dating, are not available. Like many other methods, it depends upon radioactive decay, but in this case it is the amount of radioactivity received by the specimen since the start date that is of interest, not the radiation emitted by the specimen itself. When atoms located within the structure of a mineral are. There are several more dating methods that can be used in special circumstances, but none is as important in practice to archaeologists as those already described. Some are of relevance to the solution of specific problems. Several of the most significant are mentioned below, so that the overview given in this chapter is reasonably complete. But the discussion here is deliberately kept brief, to give a flavor of a field which can easily become rather complicated, yet which is not directly relevant to much mainstream archaeology. The rather special case of DNA dating is of particular interest. 4.34, 36 Thermoluminescence dating. The TL clock in pottery is set to 0 when a vessel is fired. TL accumulates until the pot is heated again in the present day to determine its age. Glow curves observed in the laboratory. Curve displays the light emitted when the sample is first heated. Curve is the non-TL light recorded in a second heating. The extra light emitted in the first heating is the TL measured for dating. Good and bad locations for TL samples. Results will be inaccurate if the subsoil or rock near the sample at the bottom have a measurably different level of radioactivity from that of the filling of the pit or ditch. Earlier ground surface, ancient ground surface 5000. In the laboratory under an optical microscope. Since we know the rate of fission of 238U, this allows the date of formation of the rock or glass to be determined. In this case, the radioactive clock is set at 0 by the formation of the mineral or glass either in nature or at the time of manufacture, as with manufactured glass. The method produces useful dates from suitable rocks that contain or are adjacent to those containing archaeological evidence, and has been used with success at early Paleolithic sites such as Olduvai Gorge, Tanzania, providing independent confirmation of potassium argon and other results. Other absolute dating methods. Exposed to radiation from the decay of radioactive elements in the nearby environment, some of that energy is trapped. If the amount of radiation remains constant over time, then this energy will accumulate at a uniform rate and the total amount of energy will depend upon the total time of exposure. When a sample is heated to 500 degrees Celsius or more, the trapped energy is released as thermoluminescence, and the radioactive clock is set back to 0. This means that archaeological artifacts, such as pottery, will have had their clocks reset when they were originally fired. By reheating samples from these objects, we can measure the thermoluminescence released and hence date the material. The main complication of the method is that the level of background radiation that a sample might have been exposed to is not uniform. It must be measured for every sample by burying a small capsule containing a radiation-sensitive material, or by using a radiation counter. At the exact spot the sample was found. 4.37 terracotta head from Jima, Nigeria, belonging to the Nok culture. A TL reading for the age of the sculpture has provided the first reliable date for this and other terracottas from the Nok region. Height 23 centimeters. 4.38A section from the Nyawalabala I excavation, North Australia, with luminescence dates on the left and calibrated radiocarbon dates on the right. Artifact-bearing sands could be optically dated and produced results of between 53,000 and 60,000 BP, having important implications for the date of the first human occupation of the Australian landmass. 290 plus or minus 60 BP. 13,500 plus or minus 900. 30,000 plus or minus 2,400. 53,400 plus or minus 5,400. Oxide K171. Oxide K172. Oxide K166. Oxide K168. Oxide K169. Depth 100. 200. Dark gray sand. Gray sand. Yellow sand. Level of lowest artifact. Boulders. Sand and rubble. ANU 8652. ANU 8653. ANU 8654. ANU 8677. ANU 8676. ANU 8678. SUA 236. ANU 3182. SUA 237. 8,300, 8,600. 8,700, 9,300. 11,100, 12,900, 10,500, 11,300. 12,500, 13,500. 12,600, 13,000. 15,000, 16,200. C, 27,000. C, 24,000. 14 C ages. Optical and TL ages. Optically stimulated luminescence is produced by directing light of a visible wavelength onto the sample, and the resultant luminescence is measured. And once again the background radiation at the place of burial has to be measured, so optical dating suffers from many of the same complications as TL. Nevertheless, OSL has been used successfully in conjunction with TL and radiocarbon to date the very early site of Nyawalabala in Australia. Electron spin resonance dating. Electron spin resonance is a technique similar to but less sensitive than TL, but it can be used for materials that decompose when heated and thus where TL is not applicable. Its most successful application so far has been for the dating of tooth enamel. Newly formed tooth enamel contains no trapped energy, but it begins to accumulate once the tooth is buried and exposed to natural background radiation. The precision of the method when used to date tooth enamel is in the order of 10–20%, but it is still very useful for the study of early humans and the cross-checking of other dating methods. In general, the difficulties of making these measurements mean that TL dates rarely have a precision of better than plus or minus 10% of the age of the sample. A good example of the archaeological application of TL is the dating of the terracotta head known as the Jima head, from the alluvium of a tin mine near the Jos Plateau of Nigeria. The head and similar examples belong to the Nok culture, but such sculptures could not be dated reliably at the site of Nok itself because of the lack of any plausible radiocarbon dates. A TL reading on the head gave an age of 1520 plus or minus 260 BC, allowing this and similar heads from the Nok region to be given a firm chronological position for the first time. Optical dating. This method is similar in principle to TL, but it is used to date minerals that have been exposed to light, rather than heat. Most minerals contain some trapped energy that will be released by several minutes' exposure to sunlight. Such exposure is in effect the start point. Once buried, they begin to accumulate electrons once more as a result of radiation experienced in the soil. In the laboratory, genetic dating can estimate time spans in terms of human generations and only then go on to make inferences in terms of calendar years. Yet despite these limitations, it is much more than a relative dating technique and is increasingly useful. To establish absolute dates from genetic data, it is necessary to establish mutation rates for the mtDNA, Y chromosome DNA, or autosomal lineages under examination. Ancient DNA samples are compared with modern samples in order to examine branch shortening in the ADNA sample, identifying mutations that have occurred since the common ancestor of the two samples. The ancient DNA sample will have less mutations, and the ratio of mutations in the ancient sample relative to the modern one indicates the time elapsed since the death of the ancient individual in question. In the case of a 45,000-year-old modern human from Ust Ashim in Siberia, indications of Neanderthal admixtures in the ADNA sequence were compared with those surviving in modern non-African humans. Genetic contributions by the Neanderthals to the ADNA segments were expected to be longer than such segments in present-day people. As the Ust Ashim individual lived closer in time to when the admixture occurred, so there was less time for the segments to be fragmented by recombination. Chiao Mei Fu and her colleagues identified putative Neanderthal DNA segments in the Ust Ashim femur and present-day genomes, and established that the fragments supposed to be of Neanderthal origin in the Ust Ashim individual were substantially longer than those in present-day humans. Therefore, the Neanderthal gene flow, the transfer of genes from one population to another, occurred 430 generations before the Ust Ashim individual lived. Assuming a generation rate of 29 years, and that the gene flow occurred as a single event, they estimated that the admixture between the ancestors of the Ust Ashim individual and Neanderthals occurred approximately 50,000. 4.39 femur of a 45,000-year-old anatomically modern human from Ust Ashim. Genetic dating. Simulation-based models utilizing genetic data from modern populations are now available to compute divergence times for pairs of population groups. One recent computation of this kind established a date of 110,000 BP for the divergence between Yoruba and San populations in Africa. Such models show an increasing sophistication in making inferences about early demographic events and processes by using genetic data from modern populations. To 60,000 years BP, not long after the major expansion of modern humans out of Africa and the Middle East. This is clearly an important inference bearing significantly on the origins of modern humans. It is notable therefore that the framework of inference focuses on the ancient DNA from a single ancient human femur taken from the bank of the river Irtysh in western Siberia. Radioactive decay is the only completely regular time-dependent process known, uninfluenced by temperature or other environmental conditions. There are, however, other natural processes that, while not completely constant, are sufficiently steady over the course of time to be of use to the archaeologist. We have already seen how natural annual cycles produce varves and trirings, immensely useful because they give dates calibrated in years. Other processes that form the basis of the first two techniques described below are not naturally calibrated in years. But in principle they can be made to yield absolute dates if the rate of change inherent in the process can be independently calibrated by one of the absolute methods already discussed. In practice, as we shall see, the calibration for each technique often has to be done afresh for each site or area because of environmental factors that influence the rate of change. This makes these techniques difficult to use as reliable absolute dating methods. They can, however, still prove enormously helpful simply as a means of ordering samples in a relative sequence, in which older is distinguished from younger. Amino acid racemization. This method, first applied in the early 1970s, is used to date bone, whether human, animal, or shell. Its special significance is that it can be applied to material over 1 million years old, beyond the time range of radiocarbon dating. The technique is based on the fact that amino acids, which make up proteins present in all living things, can exist in two mirror image forms, termed enantiomers. These differ in their chemical structure, which shows in their effect on polarized light. Those that rotate polarized light to the left are levoenantiomers or L-amino acids. Those that rotate the light to the right are dextroenantiomers or diamino acids. The amino acids present in the proteins of living organisms contain only L-enantiomers. After death, these change at a steady rate to D-enantiomers. The rate of racemization is temperature dependent and therefore likely to vary from site to site. But by radiocarbon dating suitable bone samples at a particular site and measuring the relative proportions of the L and D forms in them, one can establish what the local racemization rate is. This calibration is then used to date bone samples beyond the time range of radiocarbon. As a means of absolute dating, the method is dependent on the accuracy of its calibration. The method